Hi everybody, this is James Tompkins and welcome to Lecture 2B of the Corporate Finance series. Now in Lecture 2A, that was also time value money in that we did single cash flows, and today I'm going to get into multiple cash flows. And by the way, to understand what I do today, you will need a solid understanding of what I did with single cash flows or in the lecture prior to this. So if you haven't gone through that or you don't feel completely, if you will, solid on that topic, then I would strongly suggest you do that first. And what I want to do is I want to start off with an outcome. Okay, so here's an example of a problem. I'm gonna do this at the end, by the way. But in my opinion, if you can do this problem, then you can do anything when it comes to time value money stuff. In other words, if you can do this problem, it tells me, and it should probably tell you, that you don't just have a memorization of this stuff. You don't just know what buttons to push and out pops some answer or whatever. It means that you're going to have a solid, in-depth understanding of this material. And if that's your goal, then I would urge you to be one of those brave souls that suffer through this whole lecture. Okay, so by the end of this, best case scenario when you see this problem is you'll be able to do it on your own. And worst case scenario is that as I go through it, you'll understand it. It'll make sense to you. And that's my goal. So if that's what you want, then hopefully I'll see you in here for the long haul. And by the way, here's another example of a challenging question. I would say this is not quite as challenging, but I'll also go through this one. So having said that, let me go through an agenda of what I'm going to do in this lecture. As I mentioned, it was multiple cash flows. And first I'm going to get into some examples of different types of multiple cash flows. Annuity, perpetuity, growth perpetuity is what we'll be doing. And then I'll be deriving formulas that relate to these cash flows. In particular, a way to take these multiple cash flows and crush them into one single number. And if that doesn't make sense at this point, you'll see what I mean in a minute. And then, like I said, while I'll do some examples throughout, I'll end this with those two challenging examples, which will bring in as many of the issues as we will have discussed by the end of this lecture. So, first of all, what do I mean by an annuity? Now, I know I keep pushing understanding, but this is a definition. And do you understand or do you memorize definitions? Well, definitions you memorize. As I've mentioned before, guess what? I don't know why the sky is called the sky. I've just memorized the sky is called the sky. And it's the same thing in this case with an annuity. So an annuity is basically equal cash flows between equal time periods over a finite period of time. So for example, here is a cash flow timeline diagram. These numbers on the bottom, those represent time periods. Okay, what do these time periods have to be? It can be anything you want them to be. They could be 1 year, they could be 1 second, they could be 2.3 years, anything you want them to be. And what is time zero? Again, anything you want it to be. Typically it's today. Okay? So if these were 1 year periods and this was today, then this would be an annuity because it would reflect $100 between equal time periods, and they're all equal cash flows, and they end at some point. So it's over a finite period of time. Now, what would I have to change in the above definition to define perpetuity? Which word? There's one word up here that I would need to change. Well, basically this word right here. A perpetuity is basically equal cash flows between equal time periods over an infinite period of time. You've probably heard of perpetual motion. What's perpetual motion? Well, it's motion that goes on forever, right? And so I guess that's where this word comes from, okay? Equal cash flows between equal time periods forever. Now, this diagram right here, okay, by the way, if you see nothing above a particular time period, that just means $0. So is that an annuity? What do you think? Yes? No? Well, actually, it is an annuity. It's just an annuity that happens to start at time period 3. I mean, is there anything in the definition of the annuity that tells you when it starts? Nothing, right? It just says equal cash flows between equal time periods over a finite period of time. And that's what it is, except this annuity just happens to start at time 3. In a similar vein, is this diagram, is that a perpetuity? It is, right? It just happens to start at time period 2. Okay, so now that we understand what an annuity is and what a perpetuity is, what I want to get into now is deriving the present value of a perpetuity. And what do I mean by that? Well, basically, for a given effective rate, okay, there exists one single number that I can put right here, I'll call it X dollars, that will make me mathematically indifferent between all of these multiple cash flows right here, okay? And so that's what the present value of a perpetuity is. It's basically crushing all of these numbers into one single number at one single time period. So that's our goal. We're gonna derive that formula. So imagine I'm given $100 today, and I deposit in the bank, and let's say the effective annual interest rate is 10%. Okay, so notice in this situation, normally, if you recall from the previous lecture, a rate that is given is what? A nominal or stated or advertised rate. Okay, well, in this case, we're jumping straight to giving you an effective rate, which means what again? The amount of interest made from $1 after one period, in this case, a year. So in this example, how much cash would you have in a year? $100, 10%, 1 year later, what do you have? $110, right? I mean, is that a single cash flow problem? It is, right? And using the only single cash flow form that exists that we derived in the previous lecture, basically 100 times 1 plus 0.1, or $110. Now, imagine that 1 period later, I say, all right, fine, I have 110. I'm going to spend $10, but I'm going to leave $100 sitting in the bank, okay? So there's the 100 that stays in the bank, and there's the $10 that I decide to spend. Okay, so I have 100 ducks in the bank now at time 1. So at time 2, what will that $100 grow into? Well, remember the rate is 10%, the effective annual rate. $100, effective annual rate. Is that a single cash flow problem? It is, right? And so basically, at time period 2, I'd now have $110. And let's say that once again, I decide to spend $10 and keep the rest in the bank. So at this point, the $100 that I began with, it has supported $10 of spending at time 1. It has supported $10 of spending at time 2. And I still have $100 in the bank. So here's my question to you, okay? Given an effective rate of 10%, could I basically continue this pattern indefinitely? In other words, could I wait a whole year, every single year, and then spend that $10 and still have $100 and just keep on repeating that over and over? I could, right? And so what that means is that $100 that I begin with at time 0 will support $10 forever given an effective rate of 10%. So what we've done is we've achieved our goal of figuring out, well, there exists one single cash flow at one single time period that makes me mathematically indifferent between all of these cash flows going on forever given this effective rate. And so what is that formula? Well, notice that the $100, the present value of the perpetuity, that's what we call this, is the $10. These are these equal cash flows divided by 10%. By the way, notice that the solution is what time period? Time 0, right? And at what time period is the first $10? Time 1, right? So we'll talk about a little bit more about that in a minute, but just make a note of that. So if I use symbols, if I call C the cash flow, the same cash flow that goes on forever, and R the effective periodic rate, so if these were 6-month periods, then I better be working with an effective what rate? an effective 6-month rate, which means what again? The amount of interest made from $1 after 6 months. And then, of course, this one single number that it crushes down into is the present value of a perpetuity. So basically, we have the present value of the perpetuity being C over R, where the solution is one time period earlier prior to the first C. So, question for you, okay? What would you rather have? Would you rather have these $10 going on forever or this $100 at time 0? Well, you might say, well, I'd rather have $100 at time 0, right? Because I'm not going to live forever, and that's actually pretty reasonable, okay? But let's assume, I know, fantasy land, let's assume that you would live forever, okay? What would you rather have? Well, you might still say, well, I prefer $100 right now because maybe I want to spend it, or maybe it just make me feel richer or whatever. And you can come up with a lot of personal reasons that are you know in particular to you, or emotional reasons or whatever. But the fact is, from a mathematical perspective, given the effective rate of 10%, is this at time 0 and all of these going on forever, are they mathematically exactly identically equivalent? They are, right? And that's what this time value of money formula does for you. So I would say that there are two traps with this formula, okay? Can you think of what they might be? Well, one is that if these are, say, 6-month periods, then this R better be an effective what? 6-month rate, right? So in other words, what I mean by the R and the T must match. If T represents the period, so if they're 6-month periods, then you better be working an effective 6-month rate. If these are 1 second periods, you better be working with an effective what? 1 second rate, which means what? The amount of interest made from $1 after 1 second. And what do you think the other trap is? Well, the solution is 1 period prior to the first C. Now, why is that the case? And why do you not need to memorize that? Well, you're not memorizing that because you've derived it. But why is that the case? Well, for us to be able to spend, when we go back to the example, for us to be able to spend that $10 when we had the original 100, did the 100 that we had originally, did it need a whole year up front to build up to that 110? It did, right? And that is when we apply this formula, that the solution will always be 1 period earlier than the first cash flow. So basically, once you've taken all of these multiple cash flows that go on forever and crushed them into one single number at one single time period, are you then free to use single cash flow principles to move it anywhere along the timeline that you want? You are, right? So for example, if these were all $10 and the effective rate was 10%, then the value of the perpetuity would be $100. Well, if I wanted to know what that $100 was equivalent to at time 1, is that a single cash flow problem? It is, right? $100, 10%, 1 year later, $110. So that's going to be the case with all of the multiple cash flow formulas that we solve for in this lecture. Step number 1, crush them into one single number at one single time period. Step number 2, use single cash flow principles to move them anywhere along the timeline that you want. So let's do an example. Okay? So let's say you receive a perpetuity beginning 6 months from today of $100 every month, and a bank pays 8% compounded quarterly. Okay? So question is, what is the value of the perpetuity today? And what is the value of the perpetuity a year from today? Okay? So, you know, what would be a really good exercise is try this on your own before we continue. Okay? I mean, I'll go through it, but try it on your own. It'd be much better for you to do this on your own if you can, and then to check the process that I go through. Now, of course, to be able to do this, as I've mentioned, you'll need to have a solid understanding of single cash flow principles that we did in the prior lecture. Okay, so let's go ahead and do this. All right, so you receive a perpetuity beginning 6 months from today of $100 every month. A bank pays 8% compounded quarterly. And what is the value of the perpetuity today? Now, before I do any finance whatsoever, I want to take a stand on the interpretation of the problem. I want to picture what's going on. So what am I going to do? Well, I'm going to draw a cash flow timeline diagram. So what do the periods have to be? Well, how often do we get the $100? Every month, right? We're kind of stuck with that, right? $100 every month. We don't change that. So the periods would have to be what? Would have to be monthly, right? And so when would if they're monthly periods, when would the first $100 begin? At what time period? Well, they begin 6 months from today. So if they're monthly periods and time 0 is today, then it would be, the first 100 would be at time t equals 6, right? And so if I picture this whole problem, here's a cash flow timeline diagram. So here's today. These are monthly periods. So 6 months later, I get my first 100. It's a perpetuity, so it goes on forever. And the question is, well, what is it worth today? Okay. Now, these are monthly periods, so I better be working with what kind of rate? An effective monthly rate, right? Which means the amount of interest made from $1 after how long? 1 month. Okay, but the information we have is a bank pays 8% compounded quarterly. So what's the first thing that we're going to have to do? We're going to have to convert that into what? An effective monthly rate, right? And so again, I covered this in detail in the previous lecture. But let's go ahead and look at that. Okay, so a bank advertises 8% compounded quarterly, and by definition, which means by memorization, first of all, this 8% compounded quarterly, what kind of rate is that? It's a nominal or stated or advertised or annual percentage rate, APR, right? And by definition, and therefore by memorization, what is the only first step that I can do with that 8%? Well, this is annual by convention, and it says compounded quarterly, so the only first step I can do with that is divide it by 4, which gives me 2%. Now, what does that 2% mean? Again, by definition, and therefore by memorization, what does that 2% mean? Well, now, by definition, I have an effective quarterly rate. And what is an effective quarterly rate? Well, the amount of interest made from $1 after how long? 1 quarter. So what this 2% means is that $1 after 1 quarter will grow into $1.02. But as we saw in the cash flow timeline diagram, the periods are monthly, right? So what kind of an effective rate will we need? Well, we need an equivalent effective monthly rate. So what is an effective monthly rate? Well, the amount of interest made from $1 after 1 month, right? Now we know that $1 grows into $1.02 after 1 quarter, right? That was the effective quarterly rate that we calculated. So how many months in a quarter? 3 months, right? Therefore, we know that $1 grows into $1.02 after 3 months, right? So here's my question for you, okay? If these are now monthly periods, and we know $1 grows into $1.02 after 3 months, does there exist an equivalent, if you will, effective monthly rate such that $1 will grow into $1.02? Does that exist? It does, right? Now, is that a single cash flow problem? Sure. I mean, here's the only single cash flow formula that exists. Again, you can go to textbooks and they'll rearrange that and they'll make you believe that there are different, here's the effective annual rate formula and so on and so forth. But the fact is, all of those formulas are nothing more but derivations or algebraic rearrangements of that formula. Okay? So which numbers go where? Okay? Using the only single cash flow that exists, what would be the future value? Well, that's the later value, right? That's the $1.02. What would be the present value? Well, that's the $1, right? That's the earlier value. What would be the R? Well, that's what we're trying to figure out, right? The effective monthly rate. And what would be the T? Well, how many periods are we bringing this dollar forward? 3 monthly periods, right? So what's the T? Well, the T is going to be 3, therefore. And so if we put in the numbers, then basically, if we solve for this RM, we get the effective monthly rate is 0.00662, or 0.662%. So if we go back to the problem, okay, now we know, hey, the effective monthly rate is 0.00662. Can I now apply my perpetuity formula if I want to? Sure, right? I mean, is this a perpetuity? Yeah, it's a perpetuity that begins at time 6, right? So which numbers go where? What would I put in for C and what would I put in for R? Well, is the C the regular $100? You know, the $100 we have every period? It is, right? And these are monthly periods, so my R better be an effective what? Monthly rate, which we've just calculated, which is right there. So basically, the present value of the perpetuity comes to about 15,100. So here's my question for you. For what time period is this 15,100 true? Well, when we derived this formula earlier, was the solution at the same time period as the first 100 or one time period earlier, right? Which one? One time period earlier, right? Now, if that doesn't make sense to you, then sorry, but you need to go back to the derivation of the perpetuity, because I don't want you memorizing that. You know, that's something you need to understand, okay? And that understanding is going to be based on going through and understanding the derivation. So in other words, if the first 100 is at time 6, then this guy right here is true for what time period? Time 5, right? So if we see that what that looks like, now we've basically said, all right, all of these hundreds beginning at time 6, okay, assuming that effective monthly rate that we calculated is mathematically identically equivalent to this 15,100 at time 5. But the question says, well, what is it worth at time 0? Well, is that a single cash flow problem? It is, right? So using the only single cash flow formula that exists, okay, here's this, the only single cash flow formula that exists, I'm just going to rearrange it for present value. And so which numbers would go where? Well, what about the FV right here? Well, that'd be the 15,100, right? That's the later value. What about the PV? Well, that's what we're solving for, right? That's the earlier value. What's the R? Well, these are monthly periods, so we better be working with an effective what? An effective monthly rate. The amount of interest made from $1 after 1 month. And then what's the T? Well, how many periods are we bringing this back? 5 monthly periods, right? So what's the T? 5 months. So if we put in the numbers, we've got 1,500. We're dividing it by something to bring it back in time, discounting. We've used an effective monthly rate. We brought it back 5 monthly periods. So this is 14,609 at time 0. So notice what we did, right? Step 1 with this whole problem was, well, we applied the perpetuity formula to crush all these numbers into one single time period, in this case at time 5. And then we used single cash flow principles to bring it where we wanted to. By the way, what would you prefer? You know, all of these guys going on forever, assuming the rates that we quoted, or this much at time 5, or this much at time 0, or are they mathematically exactly identically equivalent? Well, if you have a preference, it's outside of the boundaries of mathematics, and that's fine. It could be emotional or whatever, okay? But from a mathematical perspective, are they exactly identically equivalent? They are, right? So if we go back to the problem, okay, here's the problem. We've just calculated the perpetuity today. And what I want you to do now is, the question is, well, what is it worth a year from today? Okay, there's the answer. I want you to try that on your own. I mean, is it a single cash flow formula at this point? It is, right? We know this is what it's worth at time 0. And if we want to know what it's worth a year from today, then is that a single cash flow problem? Yeah. So try it on your own. And if you're unable to, if you struggle with that, again, I would urge you to go to the prequel to this lecture. Okay. In other words, the single cash flow principles, lecture 2A. So what I want to do now is derive the present value of an annuity. Okay, so far we've derived the present value of a perpetuity, and now we're going to do an annuity. And then we'll do one more after this. That's a growth perpetuity before we get into those challenging examples, whatever. Now, this stuff builds on itself. Okay, so we're going to derive this formula knowing the present value of a perpetuity. Now, I'll admit that with the previous one, perpetuity, C over R, that's pretty easy to memorize. And I don't want you to memorize that. I want you to understand it. But I will acknowledge that it's easy to memorize. But this one, this is going to be a lot harder to memorize. And so to really stress, if you're in my class, and if you're watching this from who knows where in the world, obviously this doesn't apply to you. But if you're in my class, it is so important to me that you understand this, that I promise you, you will see this somewhere in one of our tests, okay? Whether it's on a quiz or a test or a midterm or final or both, whatever. That's how much I want you to understand this derivation. You're going to have to teach it to me, okay? So here's our goal, okay? I've made up an annuity. Again, equal cash flows between equal time periods over a finite period of time. And the goal is going to be able to say, all right, well, what is the equivalent given one single number at one single time period? Okay, and so for a given effective rate, there exists, or I'll ask you, does there exist a single number at a single time period that would make you mathematically indifferent between all of these guys and this guy? It does, right? And that's what we're going to derive, okay? But we're going to drive it knowing, or based on our understanding that the present value of a perpetuity is C over R. Okay, so here I've made up a perpetuity. Let's say the effective rate is 10% for whatever these periods happen to be. So if these are 6-month periods, this is the effective 6-month rate. If these are annual periods, this is the effective annual rate, and so forth. So given that, can I apply my perpetuity formula to that? I can, right? So C over R, well, what would my C be? $100, right? What would my R be? 10%, right? So 100 over 0.1. And if the first 100 is at time 1, then the solution is that at time 1 or 1 period earlier. 1 period earlier, right? So basically, all of this is exactly equivalent to $1,000 at time 0. And let's say, and we could do this for any number of cash flows, but let's say I want to derive the formula for an annuity of $100 at time 1 and time 2. So it's a 2-period annuity, in other words. Okay. So what I'm going to do is I'm going to call this first line A. Okay. And I'm going to split A into 2 parts, B and C. Okay. So in other words, this 100 goes there, and this 100 goes there. So that's B, and then the line continues. Okay. So question is C a perpetuity? It is, right? So could I apply my perpetuity formula? I could, right? So we've seen the perpetuity formula is what? Well, C over R. What's the C? The C is 100. Okay. What is the R? Well, that was 10%. So 100 over 0.1 is 1,000. So that would be, the $1,000 would be true for what time period? Well, if the first 100 is at time 3, then the solution is it at the same time period or 1 period earlier? 1 period earlier, right? So at time 2. So in other words, this perpetuity right here, $100 going on forever, starting at time 3, is mathematically exactly identically equivalent to $1,000 at time 2. Okay, so who can spot the annuity? Is this the annuity? That's a perpetuity. Is that the annuity? No. What about this guy? Yeah, B is the annuity, right? Equal cash flows between equal time periods, but over a finite period of time. So our goal is to figure out B. Now, what is the relationship between A, B, and C? Well, didn't I take A and break it up into two parts, B and C? I did, right? So therefore, A is equal to B plus C, right? So here's a tough question for you. Okay, our goal is to get B. So if A equals B plus C, then B, the annuity, is what? A minus C. Very good. Okay? So in other words, this guy right here is this big long line minus this guy, right? Makes sense. Okay? Or in other words, this $1,000 at time 0 minus this $1,000 at time 2. That's the annuity. But here's my question for you. Can I subtract a time 2 value from a time 0 value? I can't, right? I mean, that'd be like subtracting euros from yen, right? You know, $1,000 at time 2 is it may as well be a different currency, right? And so I can't do that. And so what I need to do is to bring this $1,000 to time 0. And when I do that, now can I do the subtraction? I can, right? So therefore, what we can basically say is that the present value of an annuity today is equal to the present value of a perpetuity today minus a perpetuity tomorrow that's discounted to today. Now, to bring this guy back to time 0, what would I do to it? Would I multiply it by something or divide it by something? Divide it by something, right? And is that a single cash flow problem to bring this back 2 periods? It is, right? So what would I do to this? What would I divide it by? Well, 1 plus the effective rate, which was 0.1, squared. I'm bringing it back 2 periods. So basically what we have is the present value of annuity is this $1,000 at time 0 minus this $1,000, which is discounted to today, okay? So now, am I subtracting a time 0 value from a time 0 value? I am, right? And so I get this $173.55. So here's my question. For what time period is that 173.55 true? Well, what time period is this guy in? 0, right? And what about this guy? Bring it back to 0. That's 0, right? So if I subtract a time 0 value from time 0 value, what do I end up with? A time 0 value. So therefore, what we have is that we've just derived the present value of this annuity, where the first 100 begins at time 1. So we're seeing a pattern, right? I mean, when the first cash flow is at time 1, the solution is at the same time period or 1 period earlier. It's 1 period earlier. And how would you know that? Well, you wouldn't know that, or you wouldn't understand that unless you'd gone through the derivation, which is what we've just done. So question for you. What would you rather have? These 200s right here or this 173.55 right there? And again, right, you're picking up on it at this point. Yep. Guess what? They're mathematically exactly identical. So let's get into the formula now. Okay, so we saw the annuity was this $1,000 at time 0 minus this $1,000 at time 2, but we discounted it today, so all of this is at time 0. So how is the 1,000 calculated? Well, that was the perpetuity, right? And so what was the perpetuity formula? C over R, right? So 100 over 0.1. So basically, you know, if we do this longhand, we have the C over R, the 100 over 0.1, which is 1,000 there, minus, here's the 100 over 0.1, which is that 1,000 there. And if I wanted to, could I factor out this guy? I could. I mean, you don't have to do that, but if you wanted to clean it up a little bit, you could put the 100 over 0.1 there and multiply it by this 1, which is the same as this guy right here, minus this 100 over 0.1 multiplied by this 1 is the same as that guy right there. And so here we have the present value of an annuity formula. And if we add in notation, then basically, this is my what? It's what I called C before, right? My cash flow. This guy right here is what? That's the effective rate, right? So if they're 1 month periods, you better be working with an effective 1 month rate. And this guy right here, well, that actually represents the number of cash flows. Okay, let me go back a second. Okay, go back to the timeline. Okay, notice that we broke the line right here, right? And the reason that this goes back 2 time periods is because we had 2 of these cash flows. If we cut the line right here at time 3, we would have brought this back 3 periods, and we would have 3 cash flows. And so the best way for you to convince yourself of that is just to try this derivation on your own. Cut it at after 500s, and you'll see that this becomes a 5. Okay, so basically, let me fast forward here. Basically, this T right here represents the number of cash flows in the annuity. So we've achieved our goal of calculating the present value of the annuity. Again, a couple of traps, maybe at this point, because hopefully you're understanding this. These don't seem like traps, but first of all, the solution here is at the same time period or 1 time period earlier than the first C. It's 1 period earlier, right? And how do you know that? Well, you wouldn't know that unless you understood the derivation. And can you think of any other potential trap? Well, if you're working with 2-month periods, then this better be an effective what? Better be an effective 2-month rate. In other words, the R and the T, if you will, must correspond or match or however you want to put it. Okay. Now, there's one thing I want to point out, and that is there's no closed form solution when it comes to solving for R. Okay. Now what do I mean by that? Well, let me go to freehand a second. Okay, so if I write the formula for the annuity, sorry about my writing, okay, how many variables do we have there? Well, we've got the present value of the annuity, we've got C, we've got R, and we've got T, right? Now, if you recall, when it came to the single cash flow formula, okay, and just to remind you, the single cash flow formula was future value equals present value times 1 plus R to the T. Again, we had 1, 2, 3, we had 4 variables there, and I said, hey, I should be able to, or somebody should be able to give you any 3 of these, and you should be able to solve for the other, right? And so you could say the same thing for this, okay? I should be able to give you any 3 of these, and you should be able to algebraically rearrange the formula and figure out the other, okay? Well, that is true when you're trying to figure out present value of annuity, and when you're trying to figure out the C, and when you're trying to figure out the T, but it is not true for R. In other words, I cannot rearrange this formula right here and figure out, say, R is equal to something. And the reason for that is because there's an R both here and there's an R both there. And so in real life, a computer will do it iteratively, or a financial calculator, which means it'll guess at a solution and then it'll see how close it is and guess again, it'll get closer. So there's a way computers can do it. And so so basically, if you're in my class and you ever have to solve for R, then all you need to do is set up the final formula and just write solve for R. Because that way, if you don't want to buy a financial calculator, then you don't have to do that. Okay, so that tells you about the no closed form solution when solving for R. So again, what's going on here? Well, we now have the formula where we can have these multiple set of cash flows, an annuity. We can crush it into one single time period, one single number. And then once we've done that, can we use single cash flow principles to move this anywhere we want to? We can, right? And so some books, they're going to say, hey, here's the future value of an annuity formula. Well, guess what? I mean, do you really need that? And in this example, if they gave you a future value of annuity formula, if you had something that looked like this, where the first cash flow was at 1, then 2, then 3, their answer would be, all right, one single number at time 3. But do you really need that? You don't, right? Because if I understand this guy right here, can I use single cash flow form principles to move it forward 3 time periods? I can, right? So the last thing that I want you doing is memorizing any future value of an annuity formula. And the same kind of principle applies for annuity due. Okay, do you know what an annuity due is? Well, it's an annuity, and this is definitional, so it's memorization. It's an annuity that begins at the beginning of the period. So for example, in this case, you could say, all right, well, you get this cash flow up front. Okay, and again, textbooks, they're going to say, hey, you know what? Aren't we clever? Now we have yet another formula that we can have you memorize or whatever. And I'm telling you, do not memorize the formula for annuity. Why not? Well, because if I understand this present value of annuity, if I, for example, applied my present value of annuity formula to this guy, first of all, could I do that? I could, right? And if I did that, if I applied it to that, then what would my T be? How many of these cash flows are there? Well, there's 4 of them, right? So in the formula, my T would be 4. And for what time period would my solution be? Well, if the first C is at time 0, the solution is going to be at what time period? Time period minus 1. So in this example, the solution would be right here. And if I wanted to know what it was worth at time 0, could I use single cash flow form principles to move it forward 1 time period? I could, right? So again, do not memorize any annuity due formula. So it boils down to this. There's only one single cash flow formula that exists. Don't be memorizing all those other things that textbooks want you to memorize. And don't memorize a bunch of annuity formulas, okay? If you understand that essentially the annuity formula is basically a perpetuity, imagine this is a line that just goes on forever, and you just break it into 2 pieces, right? So here's the annuity that's left. So it's the big long piece, goes on forever, minus this piece, that's the perpetuity that goes on forever, but you got to discount it, bring it back to today, and you're left with the annuity. Okay, if you can picture that in your head, then you should be able to derive this, and that's my goal. I don't want you memorizing stuff. So let's go through an example. Okay, so you receive an annuity beginning 6 months from today of $500 every quarter for 10 quarters. The effective quarterly rate is 3%. So notice that's a little bit unusual. Okay, in real life, they're not going to tell you an effective rate. They're just going to say, hey, we pay 6% compounded daily, or whatever it is. Okay, so but since we've already done a bunch of effective rate problems, I'm just giving it to you right here. So the effective quarterly rate is 3%. And the question is, well, what is the equivalent amount worth today? And what is the equivalent amount worth 2 years from today? Okay. Now again, I would encourage you to try this on your own before you continue. Okay. If you have a solid understanding of the annuity, you should be able to draw the cash flow and timeline diagram, etc., and use single cash flow principles to get that. So go ahead and struggle with it on your own, or try it on your own, and I've given you the answers so you can check. But of course, I'm going to go through it also in case that helps you. So you receive an annuity beginning 6 months from today of $500 every quarter for 10 quarters, giving you an effective quarterly rate. What is it worth today? Now, again, before I do any finance, what's the first thing I'm going to do? Well, I want to picture what's going on, right? So I'm going to draw a cash flow timeline diagram. Okay, now, when do we have some kind of action going on with the cash flows? Well, quarterly, right? We get this $500 every quarter, right? So what do the periods have to be? Quarterly, right? Okay, so when's my first, if the periods are quarterly, then when am I going to get my first 500? At what time period? If t equals 0 is today, then I get my first one 6 months from today. Well, how many quarters is that? That's 2, right? And I'm going to get a total of 10 payments, right? So basically it's going to look like that. Okay, if I start at 2 and I end 11, that's a total of 10 payments. Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so 10 payments. All right, so question is, well, what is this worth today? All right, so these are quarterly periods. So what kind of effective rate had I better work with? Well, an effective quarterly rate, right? And that's just provided to us in this example. So the effective quarterly rate is 3%. So can I now apply my annuity formula? Sure. Okay, so it's what we just derived. Okay, basically a perpetuity today minus a perpetuity tomorrow that's discounted to today. Okay, and so which numbers go where? What would go here for the C? 500, right? Those are the equal cash flows. What about the R? Well, these are quarterly periods, so I need to work with an effective quarterly rate, so that's the 0.03. And what about the T? Well, how many of these guys are there? There's 10, right? So what do I need to put right here? 10, right? And so if I do that, that comes to 42.65. Now here's the important question. For what time period is the 42.65 true? Well, when was the first 500? Time period 2, right? Now when you apply this formula, is the solution at the same time period as the first 500 or one time period earlier? It's one time period earlier, right? How do you know that? Well, you know that because you understand the formula. You've derived it. And so basically this solution is going to be for time period 1. Looks like that. But the question is, well, what is all of this worth today? So is it a single cash flow problem to bring this back one period? It is, right? Would I multiply this by something or divide it by something? Divide it, right? So what numbers go where? Okay, what's my PV? Well, that's what I'm trying to figure out, right? What's my FV or later value? Well, 42.65, right? What's my R? Well, these are quarterly periods, so I better be working with an effective quarterly rate, so that's the 3%. What's my T? Well, how many periods am I bringing this back? Well, I'm bringing it back one period, right? So that's a 1. So basically, it's equivalent to 41.41 at time 0. So if we go back to where we were, this is what the value of the annuity today is. What is it worth 2 years from today? Okay, and I want you to try that on your own. I'm not even going to show you how to do it. I mean, you've got the answer, but no offense, okay, if you're in this boat, but if you cannot figure that out, then you really need to go back and look at or listen to the first lecture, okay, on single cash flow principles. That's 2A. Anyway, I hope that was helpful. Okay, so there's one more formula that I want to drive, and that is the formula present value of a growth perpetuity. Now, what do you think a growth perpetuity is? Well, the perpetuity that we talked about earlier, what was that, you remember? Equal cash flows between equal time periods over an infinite period of time, going on forever, okay? Now, because they were equal cash flows, were they growing? They weren't, right? Basically, the growth rate was 0. So growth perpetuity is where those cash flows grow at a constant rate. Okay, so for example, let's say I begin with $100 and that's growing at a constant rate of 5%. Then the next period, that $100 will grow to what? 105, right? So an example of a growth perpetuity, okay, if I begin with $100 and it grows at 5%, well, 100 times 1.05, that's 105. 100 times 1.05 squared would be what it grows to next, and so on and so forth. So this is basically what a growth perpetuity looks like that grows at 5% forever. And our goal is going to say, all right, well, how can we crush all of these into one single number and place them at one single time period? So what is the equivalent of all of this at time 0? So let me ask you this. How would you personally go about deriving this formula? Or what would one approach be? I mean, think about it, or at least as a beginning. Well, what if I brought this back to time 0 and brought this back to time 0 and basically brought all of these guys back to time 0? Once they're all back to time 0, can I just add them up? I could, right? So an approach to do this is basically, take all of these guys, bring them back to time 0, and then add them up. And you're probably thinking, well, hang on, we're going to be here all day, right? We're going to be here forever because we got these cash flows that go on forever. Don't worry, we'll figure this out. This is just a beginning. So let's begin with this first 100. Is that a single cash flow problem to bring this back to time 0? It is, right? Now, if the effective rate is 10%, let's assume the effective rate is 10%, then what would I do to bring this back to time 0? Would I multiply it by something or divide it by something? Well, I'd divide it by something, right? Divide it by 1.1, right? So there it is, this 100 times 0. What about this guy? What would I do to bring this guy back to time 0? Would I multiply it, divide it by something? Divide it, right? Except instead of dividing it by 1.1, now I'm going to divide it by what? Well, 1.1 squared. Bring it back 2 time periods. So I'm using single cash flow principles here. Okay? So if I do that to all of these guys, okay, now this form is going to look a little scary maybe, okay, but it's basically bringing everything back to time 0. Okay, so I brought this 100 back once, this guy back twice, this guy, back 3 times, etc., etc. So what I'm going to do is I'm going to call this whole thing equation 1. Okay, so at this point, your understanding should be, hey, all we're doing is just bringing all these guys back to time 0 and adding them up, and that's equivalent to one single number at time 0. So there's equation 1. Now, the next thing I'm going to do is a mathematical trick, okay? And you won't know why I'm doing it until I go another couple of steps further ahead, okay? And I wouldn't have been smart enough to figure this out. People smarter than me, figured out this technique. I think it's called recognizing the common factor or whatever. But I'm going to take equation 1 and I'm going to multiply it by this guy right here. And I'm going to call that equation 2, okay? So for example, on the left-hand side, I got x. What is x multiplied by this? Well, just 1.1x divided by 1.05, right? What about this guy right here? I've got 100 divided by 1.1 and then times 1.1 divided by 1.05. Well, what does this cancel out with that? It does, right? In which case, I'm left with 100 divided by 1.05, right? And what about this guy? Okay, if I take this, does this multiplying by 1.05 and then dividing it by 1.05, does that cancel out? It does, right? And then I've got divided by 1.1 squared, but multiplied by 1.1. Do one of those cancel out? They do, right? And if I continue the whole thing, and again, I know, scary looking, but it's what we just went through, okay? X times this is what we have here. X times that. The 100, okay, times this, but divided by that, and then divided by 1.05. So if you look at these carefully, you can see all we've done is each one of these terms we've multiplied by that. So then we have equation 1, equation 2, and this is where the trick comes in, okay? I'm going to say let equation 3 be all of this minus all of that. So on the left-hand side, we have this, something times x minus x, right? And then we have this, Okay, plus this, but minus that. Well, do those two cancel out? They do, right? Plus this minus that. Do those two cancel out? They do, right? Plus this minus that. Plus this minus the one that came before this, right? Because notice this is minus 2, this is minus 1, this is minus 1. That's okay. So basically, except for the first term, all of these guys cancel with all of these guys, except I'm left with minus the very last term. So basically, equation 3 is going to look like that. Okay, so we've got this minus x, so this minus x, and then this guy, this didn't cancel out with anything, so that, but plus this minus that. So all of these cancel out, plus this minus the previous one, plus nothing else than minus this guy right here. Okay, so maybe you want to spend a couple minutes just convincing yourself of that. So if I go on, okay, well, what is this worth? Okay, well, what's growing at a more rapid rate? The thing on the bottom or this thing on the top? Okay, now you might say, well, this is bigger than that because this is infinity and that's infinity minus 1. But is there really a significant difference between infinity and infinity minus 1? There isn't, right? What's much more important is that this is growing at a rate of 10% and this is growing at a rate of 5%. So this is getting bigger a lot quicker. And so when you divide by a huge number, what do you get in the end? A small number, right? And so to be technical, in the limit, we would say that this is going to go to 0. So this is basically worth 0, but only because the effective rate that was pertaining this problem was greater than the growth rate. So in other words, here's an assumption. That's why we have to go through derivations. You have to go through derivations because then you can understand the assumptions. And the assumptions are important when it comes to using judgment in applying this stuff. Okay? So only if the discount rate in this example, or interest rate, whatever, is 10%, is greater than the growth rate, in this example 5%, does this equal to 0. And if you assume that, then we get this, and the rest is algebra. And so if you solve for x, you would get that it's equal to the cash flow that happened at the first time period divided by this discount rate minus the growth rate. Or in this example, $2,000. If you want to convince yourself of that, then go ahead and do the algebra. And so essentially, if you apply symbols, notation, okay? If G is the growth rate and C is the cash flow at time 1, again, notice the solution is at the same time period or one period earlier? One period earlier, right? And why is it one period earlier? Well, what did we do originally with all of these cash flows when we derived this? We brought them all back to time 0, right? And so basically, using symbols, the cash flow one period later, if the solution is one period earlier, and then the discount or the interest rate minus G, and that's the equation for a growth perpetuity. So question for you, what would you rather have? All of these cash flows going on forever, or $2,000 at time 0? Or are you mathematically exactly identically indifferent? You're indifferent, right? And so once again, step 1, apply your formula to crush it into one single number at one single time period, and then can you use single cash flow principles to move this 2,000 in this example anywhere you want to along the timeline? You can, right? So again, you could argue maybe they don't feel like traps anymore to you, but you could argue there are a couple traps, okay? Number 1, this solution is at the same time period as the first cash flow or one period earlier? It's one period earlier, right? And then the other thing is that if these are 6-month periods, then this R better be an effective what? An effective 6-month rate. And again, this only makes sense if R is bigger than G. If G was bigger than R, could you apply this formula? No. And if the cash is growing at a bigger rate than you're discounting it, I mean, your answer would be what would your answer be in the end? See if you can figure that out. It'd be an infinite. Okay, you'd be rich, yay. So again, when you apply this, it's only true based on the assumption that R is greater than G. So what I want to do now is make up a challenging question, and if you're in my class, and you're probably going, yay, so glad I'm not in your class if you're watching this outside of my class, but if you're in my class, this is the level of understanding that I want to bring you to. And so I'm going to be, you can expect this kind of challenge level on tests or exams and so on and so forth. And so what I'm going to do is I'm going to simulate what I do in class. What I do in class is I make one up, and I pick somebody from the class, and usually somebody in my class has a child or has recently had a child, and so that's what I'm going to simulate right now. Okay, so let's say Jane is in my class, and she's got a daughter named Sarah. And so Jane, how old is Sarah? Okay, so she's 2 years old. All right, and do you want Sarah to go to college? Yeah, I want Sarah to go to college. All right, great. Now, when is Sarah? Is she a genius? Is she going to start college at age 10, or the normal time, age 18, or what? All right. Well, let's just assume that she's going to start college in 16 years. Okay. And let's say that the college that she goes to, let's say they're on the semester system, and it's payable, twice a year, say every 6 months. Now, do you want to send Sarah to, say, Harvard, Princeton, Kennesaw State University, Yale, one of those types of universities? Or, are we talking, UGA or Georgia State? Sorry, just kidding if you're from UGA or Georgia State. But all right, so imagine that, whatever Jane's decided, let's say the cost today is $20,000 every 6 months. Okay. And so what kind of inflation rate do you want to assume? Well, all right, so Jane says, all right, well, let's assume 3%, okay? And then just to keep things simple, let's say that the cost is frozen, okay? So once we've calculated what the equivalent is at 3% inflation, let's just say that those are that's the cost of college moving forward, okay? And so if we figure that out, and again, this is back of the envelope, this is not exact, but so 20,000 times 1.03 to the 16. Okay, so that's 3% inflation applied over the next 16 years. That comes to about 32,000. So let's just assume that the cost of college for Jane is going to, because Jane's going to pay for this, and her husband George, okay, let's just assume that the cost is 32,000 payable every 6 months, okay? And so, Sarah, are you going to let your daughter be on the 6-year plan because she gets to change her mind on her major every now and again, or are we talking about a 4-year plan? All right, say 4 years. Now, Jane, you tell me you're married to George. Now, have you already started saving? Okay. And how much have you saved up so far? All right, so let's say 14,000 is what they've saved up so far. And now these payments, 32,000 every 6 months, is a school's nice. They say, hey, take the semester and then you can pay us at the end, or do they want payment up front? They want payment up front, right? So we're going to assume payment up front. And what kind of rate do you want to assume that you're going to get on your money as you start saving? Well, let's assume 8% compound quarterly, okay? And so basically, Jane and George, they're sitting down and they say, you know what? We don't want to procrastinate. We're going to start today, okay? And we want to have all our savings done before Jane starts college. Okay, I mean Sarah starts college. Okay, Jane's the mom, and so basically, the question is, well, how much do they have to put aside on a monthly period to save for this? Okay, to achieve the college goals. Okay, So obviously, before I do anything, the first thing I'm going to do is draw a cash flow timeline diagram, right? So here's today. I'm calling time 0 today. This is what we're trying to solve for. How much do Jane and George have to put aside every single month? So therefore, these periods are what? These are monthly periods, right? And let's say 0 prime is when Sarah begins college. And so we said, or Jane and George said, well, we want to finish saving 1 month before college. Okay, so this is 1 month before Sarah begins college. So when is the last month of savings? Well, we know from here to here is how many years. We assumed that Sarah would start college in how many years? 16 years, right? So how many months is that? Well, that's 192 months from today, right? 16 times 12. So basically, the last month of savings is going to be at time 191. So are there any other cash flows that are relevant? There are, right? I mean, Jane and George, they already have 14,000 saved, right? And so this is basically, what the setup is for how much Jane and George have saved and how much their goals are if they're going to set aside equal monthly payments beginning today and ending at time 191 months. So let's look at how much they're going to have to pay, right? So here's today. Here's 0 prime when Sarah begins college. We made the assumption that college would cost $32,000 beginning in advance. So the day that Sarah starts college, they have to pay out $32,000. And then how often are they paying out $32,000? Every 6 months, right? So these are 6-month periods. And then how many of these cash flows are there? I mean, she's going for 4 years, right? So 4 years, 6-month payments. So how many of these payments are there in total? 8, right? So when is the last payment? Well, at time 7, right? Why is that? I mean, you're thinking, well, but there are 8 payments, right? Well, the first one begins at 0 prime, right? So there's this 1, 2, 3, 4, 5, 6, 7 plus this one that's at time 0. Okay, so I mean, you can look 0, 1, 2, 3, 4, 5, 6, 7. How many fingers do I have held up? 8, right? So basically, those are their payments. And so if we look at this all together, then all of this represents their savings. All of this is what they're going to fork out for the respective time periods. So the question is, does there exist a C given an effective rate such that you're mathematically indifferent between all of these cash flows on the left-hand side and all of these cash flows on the right-hand side? Does that exist? It does, right? And that's basically, by the way, have we done any finance yet? No, we haven't done any finance yet. All we've done is pictured the problem. And so what is the approach going to be? Well, basically, I'm going to crush all of these guys on the left-hand side and put them into one single number at one single time period. And I'm going to crush all of these guys into one single number at the same time period. And as long as they're in the same time period, can I set them equal to each other? I can, right? And then I can solve for C. I mean, let me illustrate what I'm talking about with simple numbers. Okay, I'm going to make up these numbers coming up. Okay, suppose the left-hand side, so in other words, all of this stuff, okay, suppose all of that came to, say, 1,000 C. It's going to be some function of C, right? And that's at time 0. And suppose the right-hand side, those are all the payments, came to $1 million at time 0. Now, if they're both in the same time period, can I set the left-hand side equal to the right-hand side? I can, right? And so you'd have, all right, 1,000 C equals $1 million. So if you solve for C, algebra, it would be $1,000. And so therefore the answer would be Jane and George, beginning today and ending 1 month prior to Sarah starting college, assuming 8% compounded quarterly, they would have to save $1,000 every month. So what I'm going to do is, that's the big picture of approaching this. So I thought I'd just show you with simple numbers first. Now we'll do it with real numbers. And you can solve for this in any time period you want. Or I'll ask you, can you solve this for any time period you want? Well, I already told you the answer. Yeah, you can, right? As long as both the left and right-hand side are in the same time period, it doesn't matter. I'm a time zero kind of a guy. So I'm going to solve for it at time zero. Okay? So these are monthly periods. I'm going to start with the left-hand side. It doesn't really matter what side you start with. So I better be working with what kind of a rate? An effective monthly rate, right? Now we're told a rate of 8% quarterly compounding. Okay? So is that a single cash flow problem to figure out an effective monthly rate? It is, right? And so try it on your own. Okay? You try it on your own, you should get an answer of 0.662%. Okay, so I'm going to let you, I won't go through this, I'm going to let you try it on your own. And if you're not sure, again, go to the lecture prior to this, okay, lecture 2A, okay, single cash flow principles, and get good at this stuff, okay? Because you have to be good at single cash flow stuff before you can be good at what we're doing right now, okay? Okay, so there's the left-hand side with my effective monthly rate. And it doesn't matter if you start with the left-hand side or right-hand side, either one's fine. But first of all, is this an annuity? Well, is it equal cash flows between equal time periods over a finite period of time? It is, right? So can I apply my annuity formula? Sure. So my C, well, in my annuity formula, that's what I'm trying to figure out. My R had better be what? Well, this effective monthly rate. What about my T? The T in the annuity formula, what did that represent? The number of payments, right? Well, how many of these payments are there? Well, if I forget about the first one, then I have 1, 2, 3, all the way through 191, so I have 191. But then I also have this one that begins at time 0, so in total I have how many payments? 192, right? And so if we look at the annuity formula, basically I'm trying to figure out C. Here's my effective monthly rate, and I have 192 of these payments. Now, for what time period is this true? Is it true for the same time period of the first C, or one time period earlier? Well, it's one time period earlier, right? So this is true for 1 month ago. Now, I told you that I was a time 0 kind of a guy, right? So I don't want this for 1 month ago. I want this for time 0. So is it a single cash flow problem to figure out what all of this is worth at time 0? What would I do to it? Would I multiply all this by something or divide it by something? Multiply it, right? Now, if I want to bring it forward 1 month, what would I multiply it by? Well, 1 plus the effective monthly rate, right? And it's just like earlier when I said, hey, $100, 10%, that grows into how much? 110, right? Which is the same as 100 times 1 plus 0.1. Well, instead of the 100, we've got all of this, which represents one single cash flow at one single time period, in this case, time minus 1. And to bring it forward 1 month, we multiply it by 1 plus the effective monthly rate. And so now we've achieved our goal of crushing the left-hand side into one single number at one single time period at time 0, at least with respect to the annuity. However, are there any other relevant cash flows? Well, we've taken care of all of these guys, right? But what about this guy? Well, we've got to count for the 14,000 at time 0, right? And can I just add the 14,000? I can, right? Because all of this is at time 0, and this is at time 0. Can I add a time 0 value to a time 0 value? I can, right? And so we've basically achieved our goal of figuring out what all of this is worth, or crushing it in one single number at one single time period as a function of c. So all of this is, if we had a c, we would have a single number at time 0. So what do we do now? Well, now we're going to do the same thing to the right-hand side. We're going to crush into one single number at one single time period and set it to what time period? Time 0, right? Why are we setting it to time 0? Well, because we've got all this at time 0. And so we're going to set them equal to each other in the end, and then solve for c. So let's move to the right-hand side. So these are 6-month periods, so I better be working with what kind of a rate? Well, an effective 6-month rate, right? So again, we're told 8% compounded quarterly. Is it a single cash flow problem to figure out the effective 6-month rate? It is, right? And again, I want you to try this on your own. You should get an answer of 4.04%, so 0.0404. And you know where to go. I've already told you, if you can't figure this out, you need to go back, to single cash flow principles, the previous lecture. So is this an annuity? It is, right? So can I apply my annuity formula? Sure. Okay. So obviously, what is the C? 32,000, right? What is the R? Well, these are 6-month periods, so I better be working with an effective 6-month rate. And what is the T? Well, how many of these guys are there? There's 8, right? So what is my T going to be? It's going to be 8, right? So that's why I have the number 8 right there. So all of that comes to about 215,000. And again, for what time period is this true? Okay, now this is going to be tricky. And if you can get this, wow, okay? Okay, you remember the 0 prime when Sarah graduates when Sarah starts college is 0 prime is also time 192 in terms of months. So when you apply this annuity formula, is it the same time period as the first 32,000 or the first cash flow, or is it one period earlier? It's one period earlier, right? So what's one period earlier than 192? Is it 191? Sorry, no, it's not 191. Because how long are these periods? These are 6-month periods, right? And so what is one 6-month period earlier than 192? 186, right? Okay, so 192 minus 6 months comes to 186. So this is true for time period 186 months from today. Now, I want this in today's value, right? I want to take all of these, crush them into one single number at one single time period, and I want that time period to be time 0. Well, is that a single cash flow problem? Yeah. I'm going to bring it back. How many periods? 186 monthly periods. Would I multiply it by something or divide it by something? Divide it by something, right? Would I be using an effective monthly rate? I would, right? Because I'm bringing it back 186 monthly periods. So if you do that, here's the effective monthly rate. I'm bringing it back 186 monthly periods, and so I get about 63,000 at time 0. So now we can put it all together, okay? All of this comes to one single number at one single time period, basically 63,000. And all of this comes to this guy, okay, which is also at time 0. So I've got one equation, one unknown. Can I solve for C? I can, right? Now, if you're in my class, when I ask this kind of level question, since I'm much more concerned with the finance than I am with the algebra, I usually say, all right, show it to me this far, and then just write solve for C. But in any case, you can go through the algebra, and if you did solve for C, you'd find that that Jane and George, beginning today, need to save $452 every month, up to and including the month prior to their daughter Sarah starting college. And by the way, if you get a slightly different answer, I've been rounding as we've been going through this problem. An answer without rounding is what you see right there. So about $449. So, just as a comment, if you can do this, wow, okay, good for you. That's great. Because if you can do this kind of problem, in my opinion, you really have a solid understanding, not memorization of this stuff. You're not just pushing buttons and out pops an answer that you're not sure where it comes from. So I hope that was helpful. Okay, let's do another challenging example. And this one's also, I would say, very challenging. You have to have an in-depth understanding to do this, but maybe not quite as challenging as this previous one. So you inherit an annuity from a rich uncle of $12,500 every 2.5 years, beginning 17 weeks from today, for a total of 8 payments. Assume a rate of 8% compounded quarterly. What is the equivalent value of the annuity today? So there's the answer, and you should try this on your own before I continue. And that way you'll have gone through your own thought process, and then when I go through it, well, if you didn't do it perfectly, maybe you'll be better off in understanding why you didn't do it perfectly. All right, so there's the problem. $12,500 every 2.5 years, etc., etc. Now, before I do any finance whatsoever, what's the first thing I'm going to do? I know you know this one at this point. Draw a cash flow timeline diagram. That's right. So here we have stuff is happening every 2.5 years. So what do the periods have to be? Well, every 2.5 years, right? So we're told 8% compound quarterly. So what kind of effective rates do you think we need for this problem? I mean, first of all, is this an annuity, the $12,500? It is, right? Equal cash flows between equal time periods over a finite period of time. And these are 2.5-year periods, so I better be working with what kind of rate? An effective 2.5-year rate. And then it also looks like when I bring it to time 0, it looks like I'm going to need a weekly period, right? An effective weekly rate. So we need to solve for an effective 2.5-year rate and an effective weekly rate. So let's go ahead and do that this time. I know in the previous problem I said, try to do it on your own, but I'll go ahead and do it here. So what is the only first step that I could do with this guy right here? And by the way, what is that guy? Is this 8% compounded quarterly, is that already an effective rate? It's not, right? How do you know? Well, that's by definition. Okay, so that's by memorization. You memorize definitions. So this is an advertised or stated or nominal rate, or APR, and the only first step by definition that I can do with that is basically divide it by 4. Why divide it by 4? Because this number here, is it annual by convention? It is, right? So it says compounded quarterly. There are 4 quarters in a year, so basically divide by 4. Now I got 0.02. And what does that 0.02 tell me? Well, it gives me the effective quarterly rate, which means what? The amount of interest made from $1 after 1 quarter, which means that $1 after 1 quarter grows into $1.02. Well, what's the effective 2.5-year rate? Well, the amount of interest made from $1 after how long? 2.5 years, right? So we know that $1 grows into $1.02 after 1 quarter, but we want to know how much it grows into after 2.5 years, which is how many quarters? Well, that's 10 quarters, right? So is that a single cash flow problem? It is, right? In fact, in this case, is it a future value problem? It is, right? We want to figure out the future value. So using the only single cash flow formula that exists, the one that you proved to me if you'd done the prequel to this whole lecture, that you proved to me you already knew is this guy right here. So which numbers go where? What do I put in for FV? Well, that's what I'm trying to figure out, right? I'm trying to figure out a later value. What do I put in for present value? Well, I'll start with the $1, the earlier value. What do I put in for R? Well, I'm going to bring this dollar forward on a quarterly basis, so I better be working with an effective what? Quarterly rate, which we've already calculated to be 2%. And what will my T be? Well, how many quarters am I bringing this dollar forward? 10 quarters, right? So what's my T? Well, it's 10. So there we have the future value of this dollar, bringing it forward 10 quarterly periods using an effective quarterly rate. This grows to 1.219. So how much of that is interest, or therefore what is the effective 2.5-year rate? Well, about 22 cents, right? Or 21.9%. So we've just achieved our goal of effective 2.5-year rate. So now we also are going to need a weekly rate. Now we've already seen that 8% compounded quarterly means we have an effective quarterly rate of 2%. And by definition, what is the effective one week rate? Well, the amount of interest made from $1 after 1 week, right? Now how many weeks in a quarter? 13, right? So we know $1 grows into $1.02 after 1 quarter. Therefore, we know $1 grows into $1.02 after how many weeks? 13 weeks, right? So if I split this quarter up into weekly periods, okay, does there exist an effective weekly rate such that $1 using weekly compounding will grow into $1.02? That exists, right? Now, is that a single cash flow problem? It is, right? So again, using the only single cash flow formula that exists, then what do I put in for my FV, the later value? $2, right? That's my future value. That's my later value. What about my PV, present value, or the earlier value? Well, that's the 1, right? What do I put in for this R? Well, that's what we're solving right? We're trying to figure out what is the effective weekly rate. And what about my T? Well, how many periods am I moving this dollar forward? 13, right? So what's my T? It's 13. So if you do that and you solve for RW, you'll get about 0.152% or 0.00152. So we now have an effective weekly rate and we have an effective 2.5-year rate. Okay, so now we can go back to the problem. So here we have today, 0 prime, 17 weeks from today. We now know the effective weekly rate is that much, 0.00152. These are 2.5-year periods. We have a total of 10 of them beginning 17 weeks from today. We now know the effective 2.5-year rate is 0.219. So I'll start off with this. Is this an annuity, all the 12,500s? They are, right? Equal cash flows between equal time periods over a finite period of time. So can I use my annuity formula? Sure. So there's my annuity formula, okay? And so what am I going to put in for the C? Well, that's 12,500, right? And what about the R? Well, what kind of periods are these? Those are 2.5-year periods, right? So I better be working with what kind of rate? An effective 2.5-year rate. Okay. What about my T? How many of these payments do I have? I have 8, right? So T is 8. We've seen the effective rate is 2.5 years. So if I put it all in there, I basically get 45,372. Now here's the kicker, okay? This will really test your understanding. For what time period is that $45,372 true? Well, when you apply this formula, is the solution at the same time period as the first cash flow, so the first 12,500 in this example, or is it one period earlier? It's one period earlier, right? And how, so this is at time 17 weeks. So what's one period earlier than 17 weeks? Well, how long are these periods? They're 2.5 years, right? So in other words, it's 2.5 years earlier than 17 weeks from today. So how many weeks in 2.5 years? Well, there's basically 130 weeks in 2.5 years. Okay, so that's 52 weeks a year. So 52 times 2.5 comes to 130. So this is true for time period t equals 17 minus 130, or t equals minus 113 weeks. So if we picture what that looks like, it looks like this. Here's today, time 0, and this solution is true for 113 weeks prior to today. So the question says, well, what is the value of this annuity when? Do you remember? They want to know, what is it worth at time 0? So is that a single cash flow problem? It is, right? I need to bring this forward in time. So using the only single cash flow formula that exists, then what numbers go where? What's my FV? Well, that's what I'm trying to figure out, right? That's the later value. What's my PV? Well, that's the 45,372, right? What kind of effective rate will I use? Well, what are these periods? Those are weekly periods, right? So I better be working with what kind of rate? An effective weekly rate. And how many periods am I bringing this forward? 113, right? So what will my T be? 113. So if we put in the right numbers, we basically get 53,894, and so that's our solution. So in other words, if you had the choice between all of these cash flows at this time period, given the rates, and 53,894 today, then would you care, or would you be mathematically indifferent? Well, from a mathematical perspective, you'd be completely indifferent. So we've done the problem, but let me give you an alternate approach, or at least in one area, an alternate approach, okay? Suppose that this guy right here was not there, so there was no $12,500 at 0 prime. Okay, just for now, just pretend that this guy is not there. Now, if that's true, then how many of these 12,500 payments do we have? We have 7, right? So, 1 through 7. So, if we then put it in a 7 right here in the formula, then for what time period would the solution be true? If the first payment was actually at 1, then the solution for this present value of the annuity would be at what time? At the same time period or one period earlier? One period earlier, right? So it'd be true for t equals 0 prime, or 17 weeks. So if I wanted to, could I put a 7 in right here and basically get all of these and crush them into one single number at one single time period, which would be at 0 prime, and then go, well, hang on, I actually do have this 12,500. Can I now add that? Would I be adding 2 sets of dollars at the same time period? I would, right? Can I add $1 from one time period to another dollar of the same time period? Well, sure. I mean, I'll illustrate. Okay, so here's $2 right now, and here's $1 right now. Are they both in the same time period? They are, right? So can I add them and get $3? I can, right? And so it's the same thing here. So I can add them because they're both in the same time period. So another way to do this problem, so you don't have to figure out, what is one time period less or 2.5 years less than 0 prime, is to say, all right, well, let's forget this guy isn't there. So we'll account for these 7, which is why I'll put a 7 there, which means that all of this is true. The annuity is true for what time period? T equals 0 prime, or 17 weeks from today. And then I go, hey, well, let me add this because I ignored it initially, and this is also at 0 prime. So I add in the 12,500, and I get 55,308. So for what time period is the 55,308 true? Well, it's true for 0 prime, right? Because all of these guys were true for 0 prime. This is already there for 0 prime. So this is true basically 17 weeks from today. So now I have to bring this back to time 0, right? Because that's what the problem says. What is it worth at time 0? Now, is that a single cash flow problem? It is, right? So using the only single cash flow formula that exists, again, which numbers go where? So what's my FV, or later value? Well, that's the 55,308, right? And what's my PV? Well, that's what I'm trying to figure out, right? What's my R? Well, what kind of periods are these? These are weeks, right? So I better be working with an effective weekly rate. And what's my T? Well, how many periods am I bringing this back? 17, right? And so if I put that in, then basically you'd get an answer of 53,894. Notice it's the identical answers we had earlier. And so that's just another way of approaching this. And sometimes it's useful, so you don't have to figure out, hey, 2.5 years earlier than 17 weeks or whatever. So in any case, those are the two challenging problems. And all I can say is that, if you've made it through the entire first lecture and you got solid on single cash flow principles, so that was lecture 2A, and you've made it through this lecture and you've paused when you've needed to, and you've practiced some of this stuff and you've done it on your own, and at this point what we just went through makes sense to you, then all I can say is congratulations, because in my opinion, you now, if you didn't before, you now have a really solid, not memorization, but understanding, a high level understanding of time value money. In other words, instead of just pushing buttons and seeing an answer, you could actually program those functions yourself. And sometimes that in-depth understanding can be very useful when you do analysis. Either way, I hope this was a good learning experience for you, and hope to see you at the next lecture. Take care. Bye-bye.